We will solve this problem as an example using branch and bound. So we solved the first LP relaxation problem. Again, LP relaxation means we ignored the integer constraint. Okay. So and then if we solve the LP, since linear programming is easy to solve, we have a pretty good algorithm. Fine. So we solve it and then we got an answer. If this answer x1 and x2, two variable has an integer by coincidence, yeah, then we are happy. Yeah, we got a optimal solution of our original IP. But as you can see here, our x1 is 8 and our x2 is 2.25, which is not integer. So we cannot say this is our answer, but we will look at our objective function value, which is 35.25. Okay, what we can know here is our original integer programming solution will have a worse objective function than this z, 35.25. So this is the upper bound because we get rid of the integer constraint. So our original IP will be worse than this one. So this will becomes our upper bound. So now we will make a branch here. So this one is just one LP relaxation problem, and we will branch out, and then we will branch. So when we branch out, since this x2 has a non-integer value, so we will branch out x2. So we don't add anything, but we will add the constraint x2 should be less than or equal to 2. So we added one more constraint from to the original problem. We add more constraint here, and we add more constraint here. So this is you can think this can be strange because we are not losing any feasible area. Since our original integer programming has a constraint, x2 should be integer, right? So I'm including 2 here, and I'm including 3 here. So we are get rid of any value from 2 to 3. Right? So it's like a 2.1, 2.2, 2.3, 2.5, 2.6, 2.7. We get rid of that area. But anyway, that numbers are not cannot be the solution of our original problem. Why I separate out 2 and 3 here? Because our solution was a 2.25. So we are expecting, not expecting, it's like hopefully our real integer optimal solution will be around close to 2, a little bit less than 2 or a little bit higher than 2. So hopefully around there. That's why we separate out there. So 2.25. So if it's going the smaller side, it will be 2 or smaller. So we are not throwing away any feasible points. And then or greater than equal to 3. So we are taking 3 or higher. So we get rid of the 2 point something area. Still, this is fine. And then we solve the LP relaxation problem again. So we added this additional constraint here, and then we solve the problem. And then we find out the solution x equals 8 and x2. This is the LP relaxation solution. X equals 2, and then we find out z is goes to the 34. This is what we call the incumbent solution because the solution is 8 and 2, both of them are integer here, and then z is 34. So far we don't know this is the optimal solution, but we find out the one feasible solution of our original problem, and then objective function is a 34. Now what we can tell here is our real z, which is the optimal for the original IP, should be smaller than or equal to 35.25 and should be greater than or equal to 34. So when we solve only these two LP relaxation problems, so we can get some idea of where our z value, our optimal objective function, will locate it. And then we calculated the gap here. And then if the gap, and then we divide by the number here, this is a maximization, so we consider this number, and then we calculated the percentage. That percentage is we call optimality gap. So some problem we can solve LP and we can get an answer, but some problem it will take a really long time to find out. So we can set the optimality gap. So optimality condition is if the gap becomes less than like a 1%, let's stop the calculating. Because the 1% gap means your solution is not the real optimal, but how good your solution is like just 1% different. So we can let the computer stop the calculation. That's what we call this optimality gap. So right now this is it's pretty good, right? 34 and 35. Maybe we can find out the better solution. It will be greater than 34. Maybe we can find out 35 of z value. So we will keep dividing. So this is the optimality gap so far. So now we'll keep doing this. And then adding this additional constraint, and we solve the LP relaxation again, then we will get an answer, which will be the x1 is 6.5 and x2 is 3. So now x2 becomes an integer, but now this is the problem. Now the 6.5 is the problem, right? Because this is not an integer. And then we find out the z is 34.5. So now I'm gonna branch out again based on this 6.5, right? Because we already have x2 is an integer. So how can we divide it? I'm gonna add one more constraint. X1 should be less than equal to the 6. So again, we dividing from the 6.5. And then we add x1 should be greater than or equal to 7. Again, we get rid of the reason, 6 point something reason. Okay. So, but still we are not losing any integer because I'm including 6 here, I'm including 7 here, so we are fine. And then we solve the LP relaxation again. And then we find out this is the not feasible, infeasible. Which means you cannot find out the solution because the original problems, you cannot have it because the 2x plus 4x2 should be less than 25, and then you cannot satisfy anything. So which means you ignore this branch. Your branch is done here. Now if you solve this LP problem, adding this constraint, which means from the original one, we already add x2 should be greater than 3, and then now we add another one, x1 should be less than 6. And then if we solve the LP relaxation problem, this one will be the x1 is a 6 and x2 is 3.25. Okay. Now we find out the z is optimal, the objective function z is 34.25. And then we can keep going on because the lower bound is 34, but this is still the greater than 34. We can branch out more. Okay, I will branch out more here, and then since now x1 has becomes an integer, but now x2 becomes a non-integer again. So I'm dividing it here, but x2 should be smaller than equal to 3, or x2 should be greater than equal to 4. Again, we are not losing any integer values here. So we find out here solution x1 is 6, x2 equals 3, and we find out the z is 33. Now we don't have to divide it again, and then we discard this one because this 33 is smaller than 34, so we don't have to dig even more. So we terminate this node, and then we terminate here because it's infeasible. And then we look at this case. So this problem is from our original problem. We get rid of the integer constraint. We add this constraint. X2 should be greater than 3, and then x1 should be less than or equal to 6, and then we add x2 should be greater than or equal to 4, and then we got the solution if we solve it as a linear programming. Now again, x1 is not an integer value, but we don't have to branch out more because again our number, so 33.5, is lower than 34, which is the incumbent solution. So we terminate this node again also. So which means we terminate everywhere. So why I didn't branch out here? Because we already have a integer value. So if you branch out means you are adding more constraints. So it will getting worse and worse, right? Here we're getting worse, but because this is the LP relaxation solution, so we are trying to find out the real, our original LP problem. This is the incumbent, so we have only one incumbent. But while you are solving and you got another incumbent, which is better than this one, your incumbent solution change, right? And then your bound will change. So now we terminated all the branch. So we can conclude this solution is the real optimal solution. Okay, so we divide the problem, divided the area. So taking out the from 2.25 into smaller than 2 or greater than 3. So of course we have to include the 2 and 3 so that we don't lose any feasible areas. And then we solve the LP relaxation. Again, we add the constraints, solve LP relaxation, and we find out this is the real optimal solution because we terminated all the area. All the case is smaller than this number, smaller than this number. This is not feasible. So this side, we cannot find out any better solution than the 34. So this is the real optimal solution. That's how Excel solver find out any integer programming problems.